For number 1, we're trying to find a polynomial that meets certain conditions, and we're told 3 zeros of the polynomial. So 3 values that when you plug them into the polynomial, the answer is 0. The result is 0. And from the factor theorem, which is on page 327 in the book, the factor theorem says that if these values are zeros, then x minus the value has to be a factor of the polynomial. So x minus -2, x minus 1, and x minus 0 are all factors of our polynomial. Now, adding or subtracting 0 never changes the value of a number. So instead of writing x minus 0, let's just write x. But let's go ahead and multiply all these factors together to try to get back to the original polynomial that is unfactored. So multiply these first two together using FOIL technique. I continue to reduce inside there. And now finally multiply through everything by x, and you get here. And we see we have a polynomial of degree 3. It has the 3 zeros that it's supposed to have, and you can double check to make sure you didn't make a mistake by plugging each of these numbers in. The result will be 0 if you plug in a -2, if you plug in a 1, or if you plug in a 0 for x. No matter which one of those you plug in, the answer is always 0. And so we're only missing one condition, and that is that when we plug a 2 in, the answer should be 32. If you plug a 2 in here right now, the answer is not 32. And so our polynomial must have some constant value that is multiplied by it that will force the result to be 32. So I'm just going to put an A here. It stands for a constant number, and we're going to figure out what that number has to be. So I know that when A is multiplied by all this, and we plug a 2 in for the x, the result is 32. Alright, so when we plug a 2 in, the result should be 32. And we're going to figure out what A will make that happen. So reduce these values inside. Reduce further. And the whole, when you plug a 2 in, you get 8. So A times 8 needs to equal 32. So A has to be 4. And so 4 is multiplied by the whole polynomial. So just distribute that through and you get your final answer. For number 2, I'm sketching the graph of this rational function. And 3.5 in the textbook discusses how to graph rational functions. And I'm going to walk through the step-by-step instructions on page 367. Step 1 says find any vertical asymptotes. So the previous page talked about finding asymptotes on page 365. And the vertical asymptotes are going to be where the bottom part of the ratio is equal to 0. And that will be where x equals -3. If you solve that for x. To find a horizontal asymptote, since our top and bottom have the same degree, they both have an exponent of 1, we look at the ratio of the leading terms. So the ratio of the coefficients here in the leading terms. And you don't see any coefficients because they each have a 1 in front of them. We don't write the 1. So the ratio is 1 over 1, which is just the number 1. So that is our horizontal asymptote at y equals 1. Step 3 says to find the y-intercepts. You find y-intercepts by plugging in x equal to 0. So plug a 0 in here for x, and we get the answer 2/3, or -2/3, so that's our y-intercept. Step 4 says to plot the x-intercepts by solving for where the function will equal 0. And so multiply both sides by x plus 3, and 0 times anything stays 0. So we're left with this. Now add 2 to both sides, and we get that x equals 2. This is the x-intercept. Step 5, we need to make sure we know if the graph will intersect its non-vertical asymptote. So here we had y equals 1. So see if this function will ever be equal to 1. So plug that in, equal to 1. Multiply both sides by x plus 3. Add 2 to both sides. And we get to this step here. And then when you subtract an x from both sides, bring that over, you get 0, equals 5. That's not true. That's a false statement, which means this original statement we started with is false. So this is never true. Our graph does not intersect its non-vertical asymptote. So with all that information, now it's time to graph. You can plot your intercepts, draw your asymptotes, your vertical and your horizontal. And then those asymptotes split the graph up into regions. And we need to just pick some points from those regions to get a general shape of what the graph's going to look like. So I picked x equals -10. This is a typo here. It says 10, but x equals -10. You plug that into the function. Just plug it in. -10 minus 2, -12. -10 plus 3, -7. So you get that value, which is close to 1.5. It's a little bit bigger than 1. So plotted a point there that's for this point, and then picked another point in that region, -4, and then when you plug that in, you get a 6, a positive 6. And then you get that shape of that graph. By those 2 points, you can see how the curve's going to look. And these are asymptotes, so the curve will keep getting closer and closer and closer to those lines, but it will never quite touch those lines. That's what an asymptote is. So draw your curve to represent that. And then I picked a couple more points from this region to, again, just see the shape of the curve. And then I drew it accordingly. For number 3, we'll be using the remainder theorem, which is on page 323 in the textbook. And we'll also be using the shortcut method of synthetic division, which is on page 321. Now, typically when you divide two polynomials, you have to do the long division process. But if you're dividing by a first degree, so x to the first power, then it's a binomial, so there's just these two terms. If you're dividing by something like this, you can use synthetic division. And so what you do with synthetic division is you copy down the coefficients from your polynomial. So the 4, the -6, the -5, and the 13. And you'd want to put a 0 in if one of these terms was missing. Like, for example, let me just cut this. If we had this, we jump from x to the third, and then there is no x squared. So we'd put a 0 in for x squared. And then we'd continue with what x to the first power is, and then for our constant term. But we have an x squared, so we just write the -6. But you want to definitely put zeros in if one of these spots is missing. And so then what we put out here is x minus the k value. So x plus 2 is the same as x minus -2. So you always want to view this value here as x subtracted something. So we're subtracting a -2, put a -2 out there. And then for synthetic division, you just bring down the first term, and then you repeat this process over and over, where you take this value, -2, multiply, and put your result. And then you're going to add those up. Do it again. Take this -2, multiply, and write your result. Add those up. Take the -2, multiply, write your result, add those up. And what you have there then is the coefficients for your answer. When you actually do this division, you would get 4x squared minus 14x plus 23, your coefficients. And then your remainder is -33. And you can check this. This actually works. If you multiply this polynomial all the way through and subtract 33, you will get that polynomial we just divided by, or we just divided into. So this last answer here, this last result from synthetic division is your remainder, and it's also the same value you get as if you plug in the subtracted value here, the -2. So if you plug a -2 into this function, you would get the answer of -33.